So thank you very much. Good morning, everyone. I'd like to thank the organizers first for bringing me here. And and also I think all the event, everything has been very well organized. My wife and I felt that we have been taken care of very well. Right. And of course, I'd like to thank Sreeni also, because he is one of the main reasons for why I'm here. And I'd like to talk about simulating turbulence, and I use the title in my title, Extreme Events. I would say actually Sreeni not only interested in extreme events, I would say he's an extreme event in itself, as far as a researcher, as far as his effect on my work, definitely. And so I'm very pleased to talk about something that he has his hands on. You'll see his imprint in some of the things that I'm going to talk about. So first, at the dinner, I mentioned that we actually had another gathering in honor of Sreeni 2.5 months ago, approximately in Denver, and I have a picture from that. And where is Sreeni? He is right here. And someday in the future, I'm going to ask him how many people he could identify. And that was a meeting in Denver. I said we had 140 people, although not everyone was in the picture. So, and let me give a very quick overview of what I have been doing. I've been doing numerical simulations. Possibly, maybe have been at that for too long, in some sense. And in recording the words spoken by Professor Navasim Herc when he opened the conference on Saturday, I think he mentioned that there was 3 types of philosophies when it comes to science, and what I do would be classified as deep science. I think I wanted to advance fundamental understanding of turbulent flows. And the questions we are interested in include the nature of intermittency. As far as the velocity field is concerned, the inertial range, dissipation range, and relating to Sreeni's lecture yesterday afternoon, I'm very interested in turbulent mixing, especially the effects of the Schmidt number. And we also look at turbulent dispersion, where we track fluid particles as well as diffusing Brownian particles forward and backward. Some of that was done with my Australian collaborator, Brian Sofford, who I think Sreeni knows very well as well. And we have been simulating, we've been trying to keep the flow simple. So we want to get a fundamental understanding at a relatively simple flow, which is forced isotropic turbulence, Taylor scale Reynolds number. The highest in our work was 1,300. We have done that at various grid resolutions. The largest production one, what I call production one, is a simulation that is several eddy turnover times long, let's say, so that we can get statistics. And the largest production one was 8192 cube grid points, reached about half a million, no, not half a million, 1/4 product processors. Recently, Dow Boria, one of my former students, he presented a poster. I think the poster is still out there. And we also have done some very short test calculations at 12K cube and also 16K cube. We have altogether about 3 petabytes stored at the supercomputer center. One of the problems that I trying to figure out is when am I going to put the data eventually someday. And my first paper was Sreeni was published in 2002. Certainly his tremendous and benevolent influence has been with me since the mid-1990s, and actually Sreeni about 10 times, as I said earlier. Though, although while we often talk about the dissipation rate, what happens to me every time I listen to him is some kind of energy production. I feeling more energetic about everything. So that is what Sreeni is very special for. And so the outline of the talk mainly talk about 3 main topics. The one is to assess the accuracy of the large simulations. It's one thing to say we have done a large simulation. The other thing is how much can we really trust the result, not to say other people might have questions for. And we'd like to look at resolution in time, space and time for so-called extreme events. This may not be a new idea. After all, who have not been concerned with accuracy? Who have not been concerned with accuracy? Everybody has, but I think recently we have had to take a more serious look at what we are doing. And also at the third part of the talk, I will talk about computing, where our main area of progress has been with GPU for the last couple of years. And within a three-dimensional homogeneous turbulence, so if you have a big computer, if you have somebody give me us 1 million core hours, not more than 1 million, let's say 100 million or something like that. What do we want to do? We can try to increase the Reynolds number. We can perform, if we keep the geometry simple, we can increase the Mach number. Professor Sanjeeva later will talk about that yesterday. We can talk about and add other physical processes or chemical processes. And then how do we recognize the limitations also? What are the deterministic as well as statistical sources of errors? And frequently we ask ourselves, if this simulation is not good enough, can we do a bigger one, a more accurate one? We solve the problems? Or somebody would ask that, well, are we going to be satisfied at some point, or we will never be satisfied? Then we have to, in order to take a more practical-minded point of view of this, though, we have to say that there will be some quantities will be good, and some quantities which will be less reliable from our simulations. So for example, the higher order moments, extreme fluctuations, they are inherently more sensitive. Now, the higher what about you want to double the number of grid points every direction? Then it's quite expensive. And can we run it long enough? That's another question. Can we sample it well enough? And so we have to. So we'd like to see whether we can get some answers about resolution in space and time without going to the effort of doing another simulation that is even larger. Sometimes we cannot do it because of the current limitations. And what about spatial resolution? Delta X, the grid space divided by Kolmogorov length scale. That's the thing that we are concerned about. We use a pseudo-spectral DNS as a highest wave number, K max, that we can resolve. And the lower resolution may be just fine for lower order statistics, velocity statistics, second order moments, and so on. But small scale statistics, and Sreeni pointed out in the paper with Yakhot, that actually the resolution requirements are stronger than what has been assumed in the community for quite some time. So what can we do? We can refine the grid run again at the same Reynolds number, more or less, and try to make comparisons. Or we can say that given a certain snapshot, we ask ourselves which features may be more subject to errors. So and take any best velocity, relatively well-resolved velocity field, let's say we truncate at some wave number. Computer statistics again has to change. If it has changed, that means that has been some errors, or that some of the properties that we observe actually are due to the highest wave number modes, which actually got not completely free of eliciting errors as far as high order moments are concerned. So the advantage of this is that this is just post-processing. We don't need to have a large do another new simulation. On the other hand, we don't have complete information from that approach either. So that's one of the things that we are doing, but not everything. In terms of temporal resolution, we have a Courant number constraint, quite appropriate. Sreeni has a position with the Courant Institute of Mathematical Sciences now. So for a three-dimensional we want to keep the Courant number below 1 if you want to maintain the numerical stability. And more or less, if it's isotropic turbulence, we can say that this is something like a certain coefficient, RMS velocity delta x divided by delta t divided by delta x. We seem to say, simulation seems to be safe to take alpha is about 12. And from there, we can calculate delta t over Kolmogorov time scale. Frequently, it's less than 1%, partly because of the Reynolds number in the large simulations. But the small scales actually go faster than that. At a certain fixed position, we find that something is happening. Is everybody here? Okay, thank you. What we find is that we have to make the time step very small. Part of that has to could be interpreted in terms of intermittency in time as well. And we are doing some short tests at several Courant numbers. So let's say starting with 0.6, multiplied by 1/2, and then another 1/2, and see what happens. Okay, so the first result here, dissipation and entropy. Almost all data sources in the literature show that entropy is more intermittent. So does it follow that that entropy will be more sensitive to resolution? We find that we need more high resolution to resolve in order to capture intermittency, the statistics of intermittent quantities. Now, however, this picture shows a different story. The lines in red are those for the dissipation PDF normalized by the mean value on the x-axis. And this line here, so this is the original simulation. We truncate it in terms of in wave number space. This line moves to that line. And similarly, the blue lines with entropy, they do change, but the dissipation apparently changed more. On the right-hand side, we have a log scales where there's an unphysical feature that can happen if the resolution is not good enough. This is suggested that this looks like the PDF picking up with power law at the extreme end, and that would imply that some moments would not exist. So there's some indications of some of the problems that we have. And so why is dissipation more sensitive to resolution than the entropy? If we look at the definitions, we see that for incompressible isotropic turbulence, the longitudinal velocity gradients, of course, contribute to the dissipation, but not the entropy. And the longitudinal velocity gradient negatively skewed, whereas the transverse is more intermittent on the other hand. So and this is we're looking at now the PDFs of the normalized velocity gradients, the red lines for the longitudinal, and then you see a relatively large change between the two resolutions. The lines in blue here, not as much, and there are now also lines in green representing the vorticity, also not as much. So there's something about the velocity gradients that we can try to understand. And what I see now is that there is an effect of incompressibility. So if we have compressible isotropic turbulence, some of these things that may not be holding. So incompressibility in wave number space implies that the velocity vector in Fourier space proportional perpendicular to the mean wave number vector. I'm sorry. So at high magnitudes of k, and so we will expect that the special content of U1, let's say, one of the velocity components, mostly in Fourier modes, where the other two wave number components are large. So what we call k perpendicular. And we can also write expressions for the one-dimensional spectra, longitudinal and transverse, in terms of based on these integrals, in terms of the three-dimensional energy spectrum function, and we can make an approximation. What about if k is very small? K is very close to k1 when k1 is itself close to the cutoff wave number, and in fact, we define delta k here is kc minus k1. And we can actually come up with expressions like that, and you take the ratio, you see that which quantities is more sensitive to the resolution. So can we have comparisons here. So on the left-hand side, E1, 1 of K1, all these lines in red, they change more than the those lines in blue, which are for the transverse velocity gradient. So what I'm saying is that the longitudinal velocity gradient is more affected by resolution, and on the right-hand side, I plot the ratio and the lines in green are the formula that obtained from the previous page, and it agrees with the data very well. And then so now, how are we going to get more accurate results? And we like to see the effects of time stepping, as I suggested earlier. So we have a relatively wide parameter space. You want to vary the spatial resolution in terms of k max theta, vary the temporal resolution, and you have 9 simulations here. How can we do 9 simulations at even 92 cube for a production time? We cannot do that. So we step back a little bit, and we'll see the two relatively, I would say, moderately high Reynolds numbers compared to other DNS. And then we had a table about delta t over tau e. These are percentages. So 0.062 means that 6 times 10 to the minus 4. And we're using one scatter second order. We should use the fourth order. Maybe we can have a higher Courant number. And so we try to get some data from get some insights from data sets like this. And the first thing here, now resolution in time. So at a given resolution in space, different lines represent effects of the Courant number. The red here and green and blue. Most of you would say, where is the green? Actually, the green and the blue are almost coinciding, almost the same. And slipping off the back of it. Okay. So what do we see for in the case of the Courant number 0.6? We see that we have much higher peak values of the dissipation and entropy. And if we reduce the time step size, they essentially go away. So that then we might conclude that those very high peak values on the lines in red are not physically realistic. And on the other hand, if we have a high Kmax ether, we'll see that the differences are not so much anymore. And also, if you look closer here, on the left-hand side, dissipation is showing a greater sensitivity than the entropy on the right-hand side. And then what about resolution in space? Now, the same data, but we plotted it different ways. So now, for each frame, by fixed Courant number, let's vary the spatial resolution. One thing that we know that if we have a high resolution, we're supposed to be able to capture finer gradients. So shouldn't we expect that the peak dissipation and entropy to be higher? Well, that's in principle that's true. In practice, we only get that with the Courant number itself is relatively low. So we have to get the time stepping errors out of the picture. Otherwise, we could be confused, or otherwise, even the larger simulation may not do us as much, may not be giving us as much benefit as we would like. And then the important question is, with in terms of time stepping, would we need a lower Courant number and a higher Reynolds number? And now we raise the Courant number, we raise the Reynolds number a little bit. And now we see that a Courant number 0.6, these three lines, red, green, and blue, they seem to be all over the place. And so we only see the Kmax ether 5.4. Only at 5.4, we see that the green and the blue are still slightly different. And also between Courant number 0.3 and 0.5, 0.3 and 0.15. So there's some indication that we may need a lower Courant number yet and a higher Reynolds number, although the effect is not terribly strong, I would say. And so what are the, then let's collect the results at different resolutions here in terms of the PDF now. The PDF normalized dissipation and normalized entropy. And the red lines here Kmax ether 1.3, 2.7, 5.4 at the lowest Courant number that we now have. And I think we can see that the data are more or less convergent. So if this is a happy situation, I think where we reduce the grid spacing, eventually we approach this state where it will not matter much anymore. And more or less the same thing also for entropy, but beware of sampling. I think the green line should not be higher than the blue line. I think that's because of some sampling issues that we can fix. We want to run some of these test simulations a little longer. And then we turn to the issue of dissipation and entropy. Do they have the same PDF, or do the PDFs eventually converge at the far ends of their tails? And so there was a paper by Mark Nelkin, 1999, showed that well, more or less because dissipation and entropy both are measured with small scale, should they scale similarly at sufficiently high Reynolds numbers? And we also have visualizations in terms of, and in addition to quantitative measures showing that, well, entropy seems to be a little different. For example, we see vortex filaments, whereas dissipation structures are essentially more diffuse. They're more sheet-like. And a couple of years ago, we published a paper where we had an 8192 kip DNS, and we showed that dissipation and entropy attain amplitudes more extreme than previously reported, scaling similarly unless average over significant scale sizes. So it seems that the results of our paper were in support of the arguments by Mark Nelkin. Unfortunately, we now have to understand that those results were contaminated by effects of time stepping errors that we didn't realize before, which we knew better earlier on. Well, because time stepping affects dissipation more than entropy, so it follows that the comparison between the PDF of these two quantities will change when we have a better resolution in time, as well as in space, I would say. And also, well, how small does the time step have to be? Delta T is 10 to the minus, well, let's say, under 1% of Kolmogorov time scale. Right? But it's still not good enough. It's still not good enough because there's the effect of the small scales affected by the large scales in the paper by Tenekis and JFM 1975. We actually have to resolve, in terms of time scale, not tau ether, but a smaller time scale Kolmogorov length scale divided by not the Kolmogorov velocity scale, but rather the RMS velocity. So that's part of the reason why we have these constraints. And now again, what do our best data tell us? Between two Reynolds numbers, now we have the red line for dissipation and the blue line for entropy. And if we increase the Reynolds number, they continue to be different, and also the peak values they increase with the Reynolds number that we would expect. The somewhat curious feature that we found was now I think we can say that both of these look like stress exponentials. Both of these curves, and they have some similarity in shape. And we try an experiment. What about if we take a dissipation multiplied by some value and generate the PDF? And these are the lines in magenta. You see that they fit rather closely. And we think that there may be a possible explanation from this, from multifactorial theory, where we assume the higher order exponents, essentially higher order, the higher order moment would be going like Reynolds number to some power. And if these two functions, f and g, have some similarity in form, then maybe you can find some empirical constant beta where we can scale these two PDFs and make them look really the same. So there's still some new understanding in it that we want to pin down a little more precisely yet. And so let me go to the third part of the talk about computing. How do we do it now, or the last 2 or 3 years, or how do we get the 8192 kip simulation? Our approach is sort of traditional. We have massive parallelism, distributed memory. Of course, we have the three-dimensional student domain. We chop it up into what we call pencils. You will divide the solution domain in two directions at the same time. And usually, most of the time, you spend in communication, transferring the data back and forth. Because if you have, let's say that if you have the solution domains where you have the entire line of data in X direction, you can take FFTs here. And now, how do you take FFT in the other directions? You have to now have some units, storage units, which are sort of vertical like that. And then most of the time we spend in the communication. And depending on the architecture, this can be overwhelming, especially the larger problem sizes. On a machine called Blue Waters, which is funded by the National Science Foundation, it's a XE6. We got a little bit lucky. We got help from consultants at Quay. They wrote some subroutines for us using the idea of remote memory addressing. Essentially, this is one-sided communication. In other words, this allows one CPU to change numbers on another CPU without explicit communication. We also helped by the machine topology. We have a large number of processors. If they are close to each other physically in the machine, then the communication would be faster. Well, however, we cannot keep doing, we have to change. We're forced to change if we want to have a handle on exascale. I spelled, yeah. So exascale in a few years. So what will exascale be like? I think now they seem to be relatively clear. Now they will be many core platforms, one CPU. So they have so-called fat nodes. What is the fat node? A fat node is the one that has a lot of memory. It's also very powerful, but it can, now it can be divided by 128 cores, 128 cores, 256 cores, maybe 512 cores, and so on. And then we also have heterogeneous computing. We try to use graphical processing units, but although there are some challenges, how we move the data are even more important, not just between the multiple CPU hosts, but also between the CPUs and the GPUs. We have some success that I'd like to talk about a little bit about turbulent mixing at high Schmidt number. Yesterday, Sreeni showed a graph which came from the algorithm that we developed. I'll say that we have had a tremendous help from Professor Toshi Goto at Nagoya Institute of Technology in Japan. Basically, we started with a space algorithm and try to parallelize it, adapt it to the GPUs. So as high Schmidt number, well, Schmidt number is a ratio of kinematic viscosity to the divisivity of the substance. For water, for heat in water, that's 7. Salinity in ocean, 700. And the smaller scale is called a bachelor scale, which is very small. And and so it's difficult to be solved. We also have very different scaling laws. We cannot simply extrapolate what we learn from, let's say, hot wire measurements of air in a wind tunnel to Schmidt number 7, or even, and certainly not the case at all for something like 700. So how do we take care of the resolution requirements? So the idea is to have the velocity and the scalar on 2 different grids with different resolution. Even we're going to use even different numerical methods. Because the scalar is going to be on a fine grid, we want to minimize communication requirements. That's where complex finite differences actually come in. And we like to see, well, let's say that we're going to say that we're going to divide all the CPUs given to us into 2 groups. One will deal with the velocity, one will deal with the scalar. So in principle, we can have some operations occurring essentially simultaneously. And also, we make the CPU work on the velocity impact, and the GPU to work on the scalar. So we have published, we have a couple of papers about algorithms. This is a journal. It's called Computer Physics Communication. We got one paper published last year. Hopefully, another. We are revising another one, and we're using the machine called Python, which so far is still the fastest supercomputer machine in the US that belongs to the official top 500 list. And so we wrote a paper based on the CPU implementation, which was actually done on the machine called Blue Waters. And so the number of grid points for the scalar field divided by the velocity field is a factor of 8 in each direction. So that means that actually, of course, the domains are the same size, but we have 512 times as many grid points on the in the case of the scalar field. So we have 2 groups of MPI processors, and we have defined what we have essentially what we call an intercommunicator transfer. So those CPUs working on the velocity field, they need to send the velocity to the scalar, well, because the scalar is driven by the velocity field. If we have an active scalar, we have to worry about transfer the other way as well. And we try to overlap operations as much as possible, velocity with scalar, or even operations that involve different velocity components. And then, well, this is a scaling plot. Professor Narasimha also talked about the concept of strong scaling and weak scaling. So here, strong scaling is same problem size. If we increase the number of processors, is the CPU time going down inversely proportional. On a log scale, there will be a line of slope -1. We do quite well here, you see, but we start to have some deviations at the larger problem sizes. And weak scaling is to stay on these horizontal lines. We increase the problem size, but increase the number of processors that the CPU, that's the time remain the same. Again, we have some challenges here at the larger problem sizes, but one of these courses in cyan, we use this approach we call OpenMP nested parallelism. Actually, we do quite well with that, and I think we are quite happy and we actually woke up a paper. So our experience are mainly based on a machine called Titan. Quay XK7. Each node has 1 GPU, and we try to avoid using CUDA. We like to use directive-based programming so that everything that we have before will still be usable, and I think probably more easily understandable. We started using OpenACC, but eventually we moved over to OpenMP, which allows a shared memory, and OpenMP 4.5. This is the 4.5. This is important. If you OpenMP 4.0 or 3 will not do what we want. Basically, we have asynchronous execution, and FFTs now become almost trivial, less than 1% of the time, because the CUDA mathematical libraries are extremely fast. But the challenge is that the one typo, memory of GPU, not CPU. So the GPU is very fast in mathematics, but the memory is very small. So we have to manage the memory very carefully. We need to minimize the data movement. So almost all operations on the scalar field are carried out on the GPUs, and want to keep the GPUs busy because they are fast. And so we have a 16-core node. We have 2 MPI processors and 8 OpenMP threads, and also more on the GPU. And NVIDIA has a visual profile which shows us very detailed diagnosis. It can show us at one instant of time what is the CPU doing, what is the GPU doing, and so forth. Currently, all the communication will go through the CPU. So there's some extra copying between the CPU and the GPUs. But on future machines, maybe we can avoid that. And so I think the numbers of this table more or less speak for themselves. With scaling, number of grid points, the number of nodes, and you'll see that the CPU time's not changing that much. Right? Especially if we turn on asynchronous execution, 2.929 to 3.259, and you see there's tremendous difference in the problem size. And the Speedup GPU to CPU is also high. It's essentially 5, which is about 2.5 faster than the minimum expectations by the system, by the people who manage the system. And so let's move towards the summary parts of this talk. And we have been looking at resolution effects and numerical challenges in time and space. And we find we were a little surprised initially. Well, we found that although dissipation is less intermittent than entropy, nevertheless it's more sensitive to the numerical issues with the role of incompressibility in it. And we have to take it as our responsibility to correct some past statements about extreme events. And then we, of course, we like, what about the other statistics? One might say, I think, what about inertial wind statistics? I've done some testing on that. I'm quite optimistic because when you look at inertial wind statistics, you're going to average over 16 grid spacings and so forth. And then now a lot of those extreme events will start to disappear anyway. And then we, based on our success with high Schmidt number simulations on Titan, we would like to, well, we have some data that we are analyzing further, and I'm sorry, I think I'm running out of time. We're going to also want to go from passive to active scalars. And for the next steps, we like to do something bigger. We have to adapt to the new machines called Summit. Hopefully, we're going to get a good handle on it. And I would say that the more people who have, we also say that we like to make the data available to any interested parties. I think that would be good for everyone. And let's say, so in addition to Sreeni's help, I need to acknowledge the sponsoring agencies, the resource providers, and other individuals who contributed to the ideas or the computing, including Darwin Boria. I think he is here. Where is it? Not sure. Okay. And also I would say one of my current students is a resident of Bangalore, Courant. And here are some publications if anyone is interested. Thank you very much.
So thank you for the wonderful talk. We can have 1 or 2 quick questions.
For larger grid size, I mean, suppose beyond 512,
Yeah.
which one is better to use CUDA or OpenSCC?
If the problem size is 512 cube.
So I'm saying 512 cube because suppose in one GPU card, the memory doesn't fit the memory requirement. So I need CPU memory as well as GPU memory or multiple GPU memory. So which one is better to use, CUDA or OpenSCC?
I think it probably depends on which programming protocol you're more familiar with. But so actually,
In terms of performance,
yes,
speed.
yes. For 512 cube, probably about the same as far as OpenACC and OpenMP.
The large grid size, which one is better?
Yes. I mean, for 512 cube, right?
512, I have used just 512, that's why I'm saying. But I'm saying about larger grid sizes, where you won't be able to fit the full memory in one GPU.
We will not. I think what we are thinking of in the future is we were going to subdivide the memory. So basically, we can think about on each node we have the CPUs, we have the GPUs, and we have the so-called PCI bus for transferring the memory. So we are trying to keep every one of these units doing something. And we actually we were initially going to use OpenACC. We were forced to move to OpenMP because there was a bug with OpenACC on the queue system that we used. We waited 2 months. Eventually, they acknowledged that it's the bug with the compiler. We cannot wait for it. But then my former student now, Matthew Clay, figured out that, well, we can use OpenMP to do the same thing. And now, according to what I know from the people in the industry, is that OpenMP apparently is going to be the major standard. So OpenACC may not be going to get future updates as much as OpenMP. I think there's going to be OpenMP 5 at the end of this year. Yeah, yeah. Yeah, so I think OpenMP at level 4 onwards started to be compatible with GPU. And they have 4.0, 4.5, and 4.5 allow asynchronous execution.
Excuse me. How about the resolution issues for the wall-bounded flows?
I'm sorry, could you speed up a little bit? I don't hear you.
For the wall-bounded flows, how about the resolution issues? For the wall-bounded flows.
Wall-bounded flow?
Near the solid wall.
Well, I'm not sure if I understand it correctly. So my work is, my exposure to simulations of wall-bounded flows were limited. I can answer the question that, well, maybe Professor Sanjeev if he would know more.
So we find that after 200,000 processors, well, till 200, so the scaling of FFT is not, it goes as n to the power minus 0.8 or so. It doesn't go as linear because of communications. FFT, parallel FFT. So what is the scaling you get with the number of nodes with your, for large number of processors? You don't have it here, but the scaling data, I mean, with the number of processors.
Yeah.
Then you need to plot, no? So that with the number of processors.
Yeah, I do that. Okay. Oh.
So
I recall one of.
So what is the slope in this?
Yeah. I'm sorry. What I recall that one of the reviewers of our paper asked me, what do we mean by scalar field processing elements? Right. I'm sorry. This is just the number of MPI. Okay, so there's a number of CPU cores working on the scalar field. And that's by far larger than the number of cores working on the velocity field. Okay. So this is a product of strong scaling. Yeah. Yes. But this is for the CPU algorithm. What about if you use GPUs? If you use GPUs, I didn't show this plot because I thought I had enough slides already. When we use GPUs, the communication gets faster. I'm sorry, the computation gets faster. The computation gets faster, which means that the communication now becomes, now it's going to take a larger fraction of the time. So your swarm scaling actually goes down. But there's nothing wrong with it because the entire simulation is still going faster than it was before.
PK, could you say something about the structure of the events that are contributing to these extreme events in terms of dissipation or entropy? What do they look like in space?
What do they look like? Well, I think it depends on the contour level. In the PAS paper, we had some visualizations. And some of those features may be contaminated by the Markov issue, but it depends. Let's say, if we look at the if our contour levels are taken at about here, then we'll probably say that the results are not too far off. Right? If we are taking a contour level way out here, then we may be in trouble. Of course, there we don't have enough samples. So I have to say, I think the more careful answer for me to give is probably we have to look at the data again. Though what we find is that at the more extreme temperature, it seems that the water filament are actually starting to get not so well organized. Maybe they're still there, but I think we have to look at that again.
Professor Yeung,
we can talk about lunch or tea break.
okay.
It's already over actually. Let's thank the speaker again.